Yeah, we'll give it a shot.
Are you sure we'll be able to record the entire class on there?
I've recorded my stellar spectroscopy class like this. Is there a 30-minute limit? Yeah. Well, how about at 30 minutes, somebody take a look-see for me, make sure that red light's still on. It's a boring lecture today anyway. If it works out, I'll post it on YouTube. If it really works out, I'll do more of them. We'll figure out how to make them better. All right, so, one more thing I'd like to mention as an announcement is, don't forget, I had that extra credit thing. We are going to get that in the books. But there was an announcement today from the acting administrator, Robert Lightfoot. Apparently, there is a new council called the National Space Council that was set up by the administration. And they had a meeting, and they really want to get down to some business. Now, one of the things that I said I would threaten to show you at the end of the semester was a movie called The Fight for Space. And in it, what I said they talk about was the fact that there was never alignment between what was going on at NASA and what was going on with the administration of the government. And so it was just plain hit and miss and hit and miss and hit and miss, and personalities got involved, etc. Maybe that's still just what's going to happen again. I don't know. But our Vice President Pence is really talking about busting some heads and trying to get some people out into space. Now, in the last administration, it was all about let's get a asteroid return mission, okay? And they were going to fly an unmanned probe out, land on an asteroid, grab some parts of it, bring it back into lunar orbit, and it's the same orbit as the moon, and then they were going to send out astronauts on the SLS, the Space Launch System, and have them get out in an EVA, an extravehicular activity, and retract or collect the space material, bag it up, bring it back in the Orion spacecraft, and head home. And it was supposed to be a mission to test all these systems. Anyway, the problem is that's happened is that a NASA engineer I once asked this question to said, the moon is red and Mars and the asteroids are blue from political alignment, red being Republican and blue being Democrat. And every time a president switches, oh, we're going to Mars. Oh, no, we're going to the moon. And so we're going nowhere. And basically, we now have a red president, and guess what? We're going back to the moon. So anyway, NASA has released information that they're going to have their Deep Space Gateway station that's going to be in a lunar orbit. They're now calling it cislunar space. And we're talking about the high ground. We're talking about getting control of this area. Guess what? The governments are using this term cislunar space. China's using it. The United States is using it. Russia's using it. The United States and Russia are entering into a collaboration with some other minor nations to build a gateway through cislunar space. They announced that the other day. This is all the new rage coming out of NASA and the government. And meanwhile, we have SpaceX and Jeff Bezos and for Blue Origins and this other company, and there's this place called Bigelow Space. They're all popping up. And they're going to be working in tandem probably with some of these parts here. We'll talk about it a little later, but NASA's big space launch system right now, the SLS, is their big rocket. It's basically a revamp of the Saturn V. And you will see that in the Fight for Space movie, everybody says, it's been almost 50 years, and we had a rocket that could get us to cislunar space, and it worked again and again and again, and we dismantled it, and now we have nothing to get us there, and 60 years later, we're just basically pulling out the old blueprints, dusting them off, and rebuilding the damn thing. That's what I call advancement. So there's a lot of people that are really upset about what's happened in this regard, and you can almost see them getting a little teary-eyed. They're so emotionally bruised by what happened over the last 50 years. So anyway, this is up here for you to read. It starts out really exciting, and then by the time you get halfway through it, at least my experience was blah, 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 promise this, promise that, we're going to do this. And I'm like, okay, you know what? I've been reading this every 4 to 8 years, new space dreams that are coming out of the talk of Washington. Never happens. I've gotten really jaded. My generation's got really jaded. Hey, but you know what? Now we got people like Jeff Bezos and Elon Musk and this guy Bigelow and I can't remember Richard Branson and these other companies, and I it's different now. There's an energy building. Okay. By the way, there's a big meeting this October, like 11 through 17, an international space meeting right there at the Farm and Ranch Museum. I wanted to go to it, but it cost $1,100. It's like, oh, but you get to see some really amazing speakers. So if you got $1,100 to burn, I'd say sign up and go hang out in the audience. Here's some real dreamers and engineers talking about this. So I'll try to get a link to that put on the announcements as well. Close down that. Okay, so. I really did log out. I thought I would talk just a little bit today about how rockets work, since that's the vehicle that has allowed us to move into this new age. So I may not talk too much about rocket scientists or science, but here's the fun thing. It's very low level, and at the very least, you can act like Tony Stark did in the Avengers when he was incredulously asked, "So when did you become a nuclear astrophysicist?" And he says, "Last night." I don't know if you guys remember that scene, but it's one of my favorites. I just studied all these specs in one night. I'm a PhD nuclear astrophysicist. Yeah. So when somebody says, "So when did you become a rocket scientist?" Right here, right now. You can go get one of those shirts, what part of, and then you got Ziakowski's rocket equation. Don't you understand? Come on, what's wrong with you? All right, so we have to talk about some physical laws. Newton discovered all these laws, or if you will, sort of like had the insights of these laws in the 1700s, had to invent calculus to come up with these laws of motion. You've probably heard of them, Newton's 3 laws, Law 1, Law 2, Law 3. Well, Law 1 is something called the Law of Inertia. I'm not going to go through with it. If you want, I can do a physics lecture too. You'd probably rather see the movie I got coming up for the next lecture. Anyway, and the second law is something called F equals ma. Force times mass equals acceleration. Basically tells you if you have a force on a massive object, it tells you basically the rate at which its speed is going to increase or the direction will change. It's very important for understanding rockets and trajectories and things like that. But it's the third law, which is the basic principle of which rockets actually behave. So, one of the first things we've got to think about here is something called temperature. Maybe I should expand this up a little bit. Okay, and turn out this light. And I have no idea what that's going to do to this video, but I hope it's still usable. Okay. Okay, so what you should always think of temperature is as something called kinetic energy, energy of motion. Okay. So when things are hot, atoms are moving around faster, and when things are cool, atoms move around slower. That is the definition of temperature, okay? Now, when atoms are moving around faster, they hit each other with harder impulses, okay? Got it? All right? If you were to be an atom and hit this wall of this container here, and you were going slow, it wouldn't be so bad. Just a little, you would deflect. But you're taking your energy and your momentum, right? And for a brief moment, you are passing it to the wall. Now, in this case, the wall is solidly and firmly implanted to not move. So that answer gets transferred back to me, and I go off at a very defined angle at a very defined speed. You see, so my energy gets basically deflected right back into me. But what if the wall could move? All right, I could hit this wall, and it might move a little bit. I would bounce off, and I would slow down because I gave it some of my energy. All right. Now, I want all of you to come up to the front of the class and start. Okay? And let's see if we can get that wall to move. Okay? Well, we're basically all going to end up in the ER room with broken shoulders in this case. But imagine if the wall could move. We could get it to move by our impulses. Okay? So that's what's happening on each of these walls. There's impulses every time an atom bounces off of it. If the temperature's higher, they're moving faster, the forces of those impulses are greater. Okay, boom. So here things are moving slow at a temperature of 200. Here things are moving fast at a temperature of 400. Okay, you get the point. Now, how does this play in? Well, let's put together the other piece of the puzzle to understand rockets, and that is this image here. For every reaction, there's an equal and opposite reaction in terms of a force. In other words, if this person here, and this is a frictionless situation where there's no friction, this person is here, they push on that boat, okay, the boat's going to push back on them, and they'll both do this. Okay? It's equal and opposite. Another thing that happens is a balloon. Now, a balloon is kind of like a rocket engine. And everybody's knocked a balloon around. Okay. So anyway, it would have been awesome if we all just screamed, "Shut up!" So here's a situation. You seal it off. The air molecules are moving around in here, just like they are in those vessels up there, and keep the balloon expanded. Okay. To let this out, now you're releasing some of it, so it's the molecules that have hit this part of the balloon up here. The balloon and it have equal and opposite reaction to each other. So the force comes up, and the particle now is pushed off the balloon the same way that the balloon is pushed off the particle. Okay? The particle ends up coming out the back of the balloon, and the balloon ends up moving upward. Particles that are moving this way, they just bounce back and forth, and they put a force on the balloon this way, but then they come back and hit the balloon that way, and the balloon stays steady. Okay? It's basically only once you open this gap here that particles that bounced off here and come out the end. And it's the bouncing, the equal and opposite reaction, that gets the balloon moving. Okay? This is how a rocket works. It's equal and opposite reaction. Okay? So here are some rocket chambers. Okay? So here we're inside this area, this rocket, and all these arrows would represent molecules that just happen to be randomly, they're moving around randomly, but these are examples of molecules that might be just heading directly into the wall, which some of them are, just to simplify the picture. And you can see that some of them are heading down and impulsing. They would push the engine down as they bounced off. Some are heading up. They would push the engine up as they bounced down. And the engine has a net zero force on it, net zero force. But you've got an opening here, and some of them bounce off the front of this nozzle. The nozzle responds, the atom responds. The atom goes out the back of the exhaust pipe, if you will, and the rocket got an impulse. Now you're thinking, wait a second. If you're an atom, and this is a Saturn V rocket on its side here, or this is a Saturn V rocket on its side, and this is the top of the engine, and I'm an atom, I mean, it's going to be like, I'm going to go flying, right? I'm just going to bounce off that thing and go flying, you know, at 100 miles an hour, and the rocket's going to get an impulse that's going to increase its speed by 0.0001% or something very, very small. You see? It's hard to get the rocket to move, but the atom, because it's so light, it's going to move very rapidly. Now, put in billions and billions and billions of atoms, and you get the rocket to go. Okay? So that's why I'm saying, imagine if this was a very, very heavy lead slab, but it was on wheels. Any one of us could come up here, and we would not really be able to see that slab move. But if you get all of us coming in, running in as fast as we can, okay, we're going to break our shoulders, but we keep coming, people keep coming here and hitting this thing, eventually this thing's going to pick up speed, and it's going to move away. So that's why a rocket starts out so slow, and then it picks up speed, okay? So everybody got the picture there on that? I got another cartoon which is kind of silly about a guy throwing bricks, which is really highly illustrative. Now, people built different nozzles to get different types of efficiency out of it, okay? There is what's called an ideal nozzle, where the gas, when it comes out the back of the nozzle, basically gets funneled so that all of the atoms are coming straight out, and that turns out to give you the highest efficiency. Okay. I'm not going to get into all these details, but I just want to let you know that people have done a lot of research to figure out what's called a specific impulse. It's a quantity which gives you the efficiency. Now, coming out of this exhaust pipe, you could put your hand there, and you would feel pressure against it. Okay? That's what they call the exhaust pressure, or P sub E, okay? But when the gas comes out, it comes out into air, into the environment. If it's in the Earth's atmosphere. If it's in the space, there is no environment, but we'll get to that in a minute. While it's in the Earth's atmosphere or on the launch pad, that exhaust pressure is having to battle against the air pressure here. Now, if you don't think there's air pressure in this room or on the Earth, you'd be sadly mistaken, because the atmosphere is pushing on you at 14.7 pounds per square inch. If you were taken into space, you would expand to the point where your body would basically, your blood would boil and it would be very uncomfortable and you would die. But the spacesuit in space isn't so you have oxygen, it's to save your body from not having atmospheric pressure on it. Okay? So, there's exhaust pressure, and then that exhaust pressure ends up battling against the air pressure here. Okay? But in space, there is no air, so the exhaust doesn't have to battle against the pressure in the air to, sort in a sense, get out of the engine. Okay? So, and we'll see where he would. What's your name, sir? Tristan? Yes. Tristan earlier was talking about the expansion of the gas coming out of the nozzle, and it turns out, for example, here is what the gas will do if the pressure of the air around the engine is greater than the pressure of the exhaust, PE less than PA, or the pressure of the air is greater than the pressure of the exhaust, then the exhaust stream gets constricted. If the pressure in the air is equal to the pressure coming out of the exhaust, then the exhaust stream is parallel lines. And if the atmospheric pressure is less than the exhaust pressure, then the exhaust will expand into the air. Does that make sense? I hope that makes sense. So when you watch a rocket launch, when you watch SpaceX launch, when you watch Saturn V's launch, you'll see they go up, and at first everything will be very funneled, and then it gets even, and then when it gets high in the atmosphere, you ever seen it? Here's the rocket, and the exhaust is doing this. Okay? That's because when it gets high in the atmospheric pressure is very small, and so the exhaust plume out of the rocket engines is expanding rapidly as it comes out. Right. I give you the rocket equation. All right? So memorize this. We're going to have several problem sets. No, I'm just kidding. So, all right. We talked about the design of a rocket, so let me define the variables that go into it. We have our fuel, we have our oxidizer, because in space you don't have combustion, so you've got to provide the oxygen. You pump those into a chamber here, and they ignite and get very hot very rapidly. They're hitting this nozzle all around. Some of them hit the back of this nozzle, give it an impulse, and they come out through here and come out of the exhaust chamber. Okay? Now, the rate at which those particles come out is measured in how much mass is moving. That's what this m dot means. It's the mass flow rate. How much mass of these atoms in the exhaust are passing through this area per second. Okay, m dot, it's a calculus term. You also have the size, or the area, of the exhaust nozzle itself. Okay, basically it has a radius, and it's pi r squared. It gives you the area of that surface, imaginary surface that the gas is passing through, the nozzle area. Okay, it's the round, it's the area of that circle of the nozzle. Okay, the gas comes out, and it comes out at a certain velocity, the exhaust, and it's coming out again. If you could hold your hand there, you would feel the pressure. It comes out with some pressure in the exhaust, P sub E. Okay, when it comes out, what do they call it? E, exit. Okay, fine. When it comes out, it's coming out into an environment which has some pressure, zero, pressure not pressure for the atmosphere. They call it sub-zero. Okay, P naught. So P is pressure, m dot is the mass flow rate, and then V is the velocity of the exhaust. Okay, so now what they're saying is the thrust force, the force on the back of this chamber that's going to move and accelerate that rocket, okay, thrust force F, is take m dot, the mass flow rate of the particles, times their velocity of exit, okay, and that actually is going to provide a significant amount of that thrust. Okay, but there's one more term, and it turns out that pressure times area is force too. So you take the pressure of the exhaust and you multiply it by the area over which it's coming out, and you got these two terms, and then you have to subtract off the fact that it's pushing it and battling to get out against the atmosphere. Can everybody hear me when I'm teaching to the screen? Sorry about that. All right. So maybe a better way to think about this, I'm wondering if I can be smart enough to raise that screen. I think it's above my pay grade. Oh, look at me. What genius are you? Stop. All right. Maybe the better way to write this, please work, please work, please work, is that the thrust is equal to m dot times v sub exit plus the exhaust pressure times the area of the exhaust nozzle minus the pressure of the atmosphere times the area. In other words, you end up reducing your thrust by how much you have to battle against the atmosphere. So if you're not in the atmosphere, you're in space, this term goes away. And this is the rocket equation. M dot VE plus P PEAE. Okay? And you'll notice that this is the biggest the term can be. But if you are in the atmosphere, and so the exhaust has to battle against the atmosphere, you have to subtract off that term. And you get a thrust value now, because you're subtracting off this number, that is smaller than it would be if you were in space. That's my point. Rockets are more efficient in space than they are in the atmosphere. If anybody says to you and you say to them, well, if you say this to them, you're going to get out of the class. But if they say it to you, and you ask them, how does a rocket get off the launch pad? And they say, well, the exhaust pushes it off the launch pad. Oh, really? Okay. So when it's in space, what's it pushing off then? Gotcha. Okay. So it's not pushing off anything. The gases in the back of the rocket are pushing the rocket. They're getting pushed out the back, and the rocket's getting pushed. Okay. And if you're in space, there's no atmosphere to battle, so that goes away, and you get the best thrust available that the rocket can give you. But if you're in the atmosphere, you got to add that term. And so while you're in the atmosphere, the rocket's not working as good as it can. It's not 100% efficient. That's what I wanted to teach you today. And Tsiolkovsky figured this back out in the 1890s, before rockets ever existed. So you got to tip your hat to the quaint little mathematics teacher from the very poor Russian village that he grew up in. Boy, when somebody lifts that screen up, they're going to get a surprise. Somebody was teaching engineering here. Okay. So here is the, again, one more time, the idea of the fuel coming in, getting into a pump, the oxidizer coming in, bringing into a pump. Then you get the chamber, boom, they're pushing, all the atoms pushing this way, bounce off this way too. There's no net force in this direction. The ones that hit there are released out the back, so there's a net force, pushes the rocket up. Later on, they realized this thing got really hot, and it was very hard to keep it from destroying itself. So I can't remember who invented this, but I know they used it for the Saturn V. They got smart. One of the things is these are super cooled, so they had to actually heat them before they go in here to the chamber to make the rocket more efficient. They preheat them. So what they decided to do was they would have the fuel pump from the oxidizer or the fuel come down and pump the liquid cooled materials around the nozzle. This did two things. It cooled the nozzle and heated the fuel, and then they bring it back into the turbine and bring it into the custom chamber preheated, and it's more efficient. That was a very brilliant idea that happened, and I'll show you these. Here's the Saturn V. This is the most powerful rocket that's existed, and you can see the cooling rings here around these engines. Okay, anybody ever been to Kennedy or Johnson and seen this baby? Yeah, it's spectacular, isn't it? I mean, it's so big, it's hard to fathom how powerful this is. Each one of these engines is putting out thrust. Remember that equation we just calculated? Of 1.5 million tons. Each one. So together, these 5 engines are putting out 7.5 million tons of thrust. Charles Lindbergh sat down with the Apollo 11 astronauts and asked them really quickly how much thrust was produced in the rockets, about 7.5 million. And Lindbergh said, in the first second that those engines are ignited, before the rocket has even left the ground, you'll have burned more fuel than I did when I flew across the Atlantic by myself. I know, may not put it in perspective, but in those days, for Charles Lindbergh, who did that amazing feat, it really put it in perspective. And they have to go 240,000 miles and break out of the Earth's gravitational field, so they have to carry a lot of fuel. Okay. Now, so yeah, this is the Apollo rocket. So Again, if you get a chance to watch the movie Apollo 13, you get a really good feeling for that. Now, one of the rockets we're going to spend some time talking about is the, in a sense, the mother of all rockets, the V2, or Vengeance Weapon 2, as Hitler called it. And it was a very simple device to deliver an explosive in something that was called the payload. Payload is the name. Basically, you pay for that load. I guess that's where it came from. People joke about that, it takes a lot of money to put something in space, so you have to pay a lot of money. You put it up there, and it's the load, and so you get it. Okay, so anyway, they had some guidance systems up here, which were very rudimentary in those days. And then they have, of course, the fuel and the oxidizer, and then the pumps and the nozzles to do that, and out it came. Back in those days, they used fins here to help guide the missile. All right. Later on, they developed something called gyros. Now, I'd love to talk about gyros because I'm a physics geek, but I'm not going to do that right now. Okay, so here are the two competitive rockets for the moon race. Now, don't let anybody fool you that the Soviets weren't fully engaged in a moon race. They had everything planned out, including how they were going to get there. They had the training of the astronauts all in place. The problem is this rocket, their rocket, which is called the N1, never was successful. They fired it 4 times, and each time it basically blew its brains out. And one of the accidents was so bad, it lost 150 engineers and high-level officials. They were just incinerated in this explosion on the launch pad. Of course, it was all kept secret in those days, and we didn't know about it. Now, I just told you about the Saturn V, and it has these 5 F1 engines, which each have 1.5 million pounds of thrust. The Soviets could not build engines like this at the time. And it turned out that the Americans almost failed at building these engines. It almost was a showstopper for the Saturn V. But they solved it. But the Russians took a different approach. They said, no, let's keep our smaller engines that we know work, and let's build them into a big constellation of engines. I think there's 36 of them here. And then we'll use that to power the rocket. Now, the thing that was so complicated about, whereas they only had to have 5 valve systems and fuel pumps, 1 for each engine, they had to have 36. And they all have to work simultaneously. And sometimes this rocket failed because 1 or 2 of these inner engines would fail. And it turned out that they didn't have the money or take the time, because they were under so much pressure, to do static ground tests to actually test what that would do dynamically to the rocket. Well, guess what it did dynamically to the rocket? And off she went. So they had a lot of problems with that. Anyway, if you now will move forward to starting to read the Space Age book by Dana Cadbury, I think it is. I really recommend you get started on that book, because it's really going to talk about the next 5 weeks of class in great detail. And you're going to learn a lot of stories about these people that we're going to talk about in the lecture that's coming. So what I'd like to know, I guess I don't have my my little guy throwing the bricks picture in this lecture. I had it in another lecture, but I think you guys all got the point. Are there any questions about rocket scientists? Now you all know that there's a rocket equation, how it basically works in principle, and that rockets are most efficient when they're firing their engines actually in space when there's no atmosphere. Yes, sir?
How often do they actually have to fire their engines in space to continue moving? Like, what would cause a speed decrease if there's no atmosphere?
Okay, that's a great question. So it turns out that once they get the rocket out of any discernible atmosphere, there is no friction against it. And so you don't have to constantly burn the rocket to get from point A to point B. We'll find out a great deal is that let's say there's what you call burns, and they burn for maybe 2 minutes, 30 seconds, or 4 minutes to get the rocket pointing in the right direction and going the right speed, and then they turn off the engines, and the rest of it's coasting. Okay, and we'll talk about, I think, something later called a Hohmann transfer. Yeah, we will. So when they get into Earth orbit and they want to go to the moon, they have a command that's called TLI, called Trans-Lunar Injection. And that was one of the most exciting moments in Apollo 8, of course, because that then, for the first time, you're going to fire the engines to leave Earth, for real. And they got the command, you are go for TLI. They fire the engines for about 3 minutes, 4 minutes, and they get up from 18,000 miles an hour up to 24,000 miles an hour. And then they turn off the engines, and the rest of it is just coasting to the moon. Now they're coming in at the moon. They're slowing down a little bit as they go, not because of friction, but because of the gravity of the Earth pulling back on them. So they're slowing down. But then they get through the halfway point of gravity, where the gravity is equal from the Earth and equal to the moon. Then they start speeding up again because now they're being pulled in by the moon. By the time they get to the moon, they're going about 5,000 miles an hour. So to leave Earth and get here took 24,000 miles an hour. Then the speed slowed down. Then it sped up 5,000 miles an hour. Then guess what they do? They turn their butt to the direction they're going, and they do something called a lunar insertion burn. And they, for 4 minutes, fire the rocket going backwards to slow them down to about 2,000 miles an hour. And they get captured by the moon and go into orbit. So it's really a matter of short burns that are strategically placed and timed. Rocket science. Yes?
So I don't really know what a static burn is.
A static burn.
A static burn test on the ground. Can you explain what the idea is there?
Yeah, thanks for asking, because I've just been throwing that out. They do a lot of these out at White Sands, actually, on the ones that's to the north on this side of the mountains. And it's basically a cement structure that they put the engine in. And they hold the engine in place, and then they ignite it. And basically they're measuring how many pounds of thrust are they getting out, how well is the flow. You know, they're basically doing all the engineering tests on that engine. How hot did things get? What was the temperature in the core of the nozzle, etc., and trying to get up and make the engine the most specific that it can. So that's why they call it static burn, because the engine's held in place, and then it's basically an all-up engineering test. Then they go back, they review everything, maybe make some tweaks, and do it again, and try to make that engine the most efficient they can.
I think we talked about it last time, right? When they did the Falcon Heavy static.
Yeah, they did the Falcon Heavy. I think we showed it. Yeah. I mean, in the end, it was just basically you're watching all this exhaust go, and it stops. Now, to us, that's all we see, but to the engineers, they're collecting loads of data on every part of that engine. Yeah. Yes, sir, in the back.
What was the program during the Challenger disaster?
We are going to have quite a bit of lecture on that later in the semester. But in short, what happened there was...
Could you repeat the question?
Oh, I'm sorry. What happened with the Challenger? Why did it explode? So let me just show an image of the space shuttle. Okay. So if you have seen the space shuttle before, basically you have the orbiter, and then you have the external tank. The external tank has the oxidizer and the fuel for the 3 engines that are on the orbiter itself. And then tied to that are 2 solid rocket boosters, okay? And these come in segments, as you can see, okay? Now, so what happens is the solid rocket boosters and the engines on the shuttle itself all ignite for liftoff. And these are super powerful, and they're very dangerous. You can always see how dangerous they are? So you can always turn off. You can always turn these engines off because they have valves and controls, right? And throttles. these do not have any throttles. They're like, they say that once you ignite this candle, it burns until it's out of fuel, and it's got this sort of liquid gel fuel in it, okay? So once you ignite these things, they burn until they're done burning, and that's all you have to it, and they're very powerful. Turned out this was a bad design that came about because of budget cuts. Just saying that. Now, these segments are put together, and you have to stop this tremendous pressure of this fuel expanding and burning from leaking out between these segments. And in short, what happened is there was a leak that formed in the inner region of one of these segments. It's a little bit lower down here, and a little flame came out, and the flame then burnt a hole in the external tank, and then it just went kablooey. And so that's what happened, and that happened about 78 seconds into launch. Okay, so, but we'll talk more about that a little later. Yeah.
Wasn't it because the Russians were doing the measurements and didn't convert them correctly?
Oh, that's a different failure.
Oh.
That was a different rocket. That wasn't. I don't think that was a manned rocket, actually. But there was one where that somebody designed the program for the computer in metric, and the gauges on the machine that were sending data back were British, and it got confused, and they had to blow it up before it really launched. Too far up, and yeah. Right. But what happened here was that they launched in too cold of weather, and so the little seals here were not very pliable. They were too hard, and they got burned past. O-rings, right? The O-rings. And then we have the Columbia accident, which is a whole nother accident, which we're not going to get into today. All right, so let's move to Cold War rocketry and set up the space race. The space race started, as we know, 60 years minus 1 day ago with the launching of Sputnik. So we'll talk about that. So we're going to talk about World War II and the end of the World War II and how it set up the Cold War. Basically a bipolar political alignment of the planet, geopolitical alignment, and we're gonna introduce the concept again of another Iron Curtain, kind of similar to what we talked about with the Muslims during the period that was lifted during the period of the Mongolian expansion. Okay. And it turns out now that rockets have been developed and nuclear warheads have been developed. And the race is on to have the most protection or offensive ability, first strike capability with this new technology. And space becomes this new battleground. And it turns out there's a visionary in Russia named Sergei Korolev who, against all odds, convinces the brass, basically the premier of the Soviet Union, hey, let me put a small radio and scientific instrument on the top as the payload of one of my rockets, and we'll put it into space. And Khrushchev, the leader of Russia, thought, oh, this is stupid, but I'll let you do it. And it turned out to be an international sensation that started the space race and scared the crap out of America. Okay. Anyway, delivery systems and nukes, intercontinental ballistics. And then one day they threw this ball into space and everything changed. See there it says space race. Start reading. Okay. Now, everything I'm going to tell you is reviewed in a movie that I'm going to show you next Tuesday. It's a sequence. It's called Space Flight, and I'm going to break the movie up into small bite sizes. And this movie is going to basically take everything I'm telling you in lecture, but it's going to have real interviews from the people, and it's going to have real footage of the launches, and it's really fun to see. Especially, there's this moment of this old guy. He's gray-haired, sitting in a chair. He's got glasses on it, that look like they're 7 inches thick. You can see his eyes are all distorted. And he seems like this old guy, but he was your age in World War II, and he was there at the launching of the first successful V-2 rocket on October 3rd, 1942. Now, I don't know what it is about early October and rockets, October Sky, the movie, and, October 4th, Sputnik, October 3rd, the first V-2. Neil Armstrong should have landed on the moon in October. But anyway, this old man almost falls out of his chair talking about how exciting it was to be there on the day that humanity had changed, and how everybody was walking around after this rocket launch just, oh my gosh, we have entered a new age. We have transformed humanity. I mean, even though it was a weapon of war, the people that were working on it understood this. And it's amazing to hear this person. I love that interview. His name's Kraft Erica. But also, you're going to see a lot of German innovation in terms of rocket cars and stuff like that. It's very fun. But Wernher von Braun first built something called the V1, which was known as a buzz bomber. And it actually had wings, but it had a jet engine, and it was sort of, in a sense, the first unmanned drone with a bomb. And it basically, they shot it across the English Channel, and it would come down and explode in London. Now, the thing about that was that you could hear that engine because it wasn't supersonic. And people could hear it and then run for cover. With a V-2 rocket, you'll see in some of the interviews, it was said, the only reason you knew that a V-2 rocket had gone off was because you weren't dead from it. Because it came out of nowhere silently and exploded, okay, coming in supersonically, okay. So here's this picture of this beautiful thing. You can see they lined up many of these rockets. They shot them over on London. It was a last-ditch, desperate attempt by the Nazi regime. As you'll see in the book, because it tells the story beautifully, Wernher von Braun joined the VFR, Rocket Club, with Hermann Ober. Here he is as a young man. Was approached by the military, and eventually, in his late 20s, was an amazing manager, engineer, leader. He became the leader of an entire facility like this in his early 20s. And he turns out his brilliance wasn't just in rocketry and in his rocket science brain, but he was an amazing manager. He was a person who got people to really believe in what he was doing. He was a very inspirational and charismatic person. Again, these are key things when new things are being developed. Getting people to believe in what you're doing and have that passion. Okay. Turns out that he got in a lot of trouble, and it's all written up in the book. He got thrown in jail. His project finally got taken over by the SS and Heinrich Himmler, and then he got arrested by Himmler for talking about putting men in space instead of building, rockets for war and things like this. But he was released finally, and then had this amazing, gutsy experience and journey to get to the American lines. I just can't tell you the whole story in here. It's in the book. And I'm telling you, it is scary. This is a situation where he had 10 orders on his desk, and 5 of them said, if you don't destroy everything in place in Peenemünde right now, you will be shot. And the other 5 said, if you do not pack up and move everything from Peenemünde to some other place, you will be shot. I mean, the guy was between a rock and a hard spot. And he got his engineers together, and they built fake trucks with fake signs on them to make them look like they were part of a military project. They forged papers, and they tried to get through Germany to the American lines in a period of time of chaos when people were just being shot for looking the wrong direction or looking wrong. And there were several times they were at border stops. They almost got busted. It's an amazing story. It's all in the book, and it's really worth reading. And if you can just imagine what the fear factor must be every time you turned around the corner in the road, what's coming up in the next quarter mile. Anyway, they finally made it, and here he is in the United States later, showing off his V-2 rocket. Now, the author of the book kind of once in a while lets their personal opinion about Werner come out, saying he should have been tried in Nuremberg as a war criminal. Now, you'll find out why in the book, and it has to do with the fact that about 5,000 people died in slave labor camps building the rocket. The question was, how much a part of that was Werner von Braun? Anyway, we had something called Operation Paperclip. Okay? It's described in great detail in the book, and basically, we picked the best, the top 150 of the rocket science team. We grabbed all the documents that they'd saved and buried. Oh, the story of that is amazing. We got them out of the tunnels like hours before the Russians came, because that was in Russian territory, and there was a time that was designated for the transfer. They just got those things out of there. I'm telling you, the stuff is espionage stuff at its best. Okay. Anyway, here they are in Fort Bliss. Okay. Just down the street. All right. And here we are at White Sands launching a V-2 rocket just down the street. Now, I loved it. Somebody in the extra credit said, one of the things that stuck with me in this class is, go forth or be carved up. Right? And I loved it. So if that's you, I'm tipping my hat to you. Here's Germany all carved up. Okay. So here's the Russian zone. They came in through Poland. Berlin is here. It was split up and carved up. And then we have the British zone, the French zone, and we have the United States zone. And then here's the Russian zone and British zone again. So all of Peenemünde was up here. So all this stuff had to come down through here and then be moved into the United States zone. Berlin itself was cut up into 4 spots as well. There was a Russian side, and then there was a British, French, and American or United States zone as well. Eventually, Khrushchev built a wall across the German zone, and it becomes the Berlin Wall, and then eventually sets up an Iron Curtain all the way across Europe. And really, it split everything. The United States put something together called the Marshall Plan, which is was to funnel money into these states so they could rebuild themselves and get some infrastructure so that we could actually build this up again so that we had strength against this building pressure from the communist zone. So now I'm going to share with you the father of Sputnik, the father of the first true ICBM, Intercontinental Ballistic Missile. A missile that could reach halfway around the world and deliver a 5-ton nuclear weapon into the United States as early as 1957. We had no defense against this. Zero. Okay. Now, interestingly, whereas von Braun was treated like a royalty at some level until Heinrich Himmler got a hold of him, threw him in jail for a while, and then made him basically kind of a serf to the SS. He was never really struggling like Sergei Korolev did. Okay? I've read this guy's biography. It's a fantastic story of a young boy growing up, being excited, developing gliders, winning contests, becoming a pilot, going to school, becoming an aeronautical engineer with hopes and dreams, joining rocket clubs, forming rocket clubs, and then getting the attention of the government, and then getting in charge of government facilities, and then getting involved in petty rivalries with other Russians that are ranking officials that wanted to take his position from him. And they had these things called the Great Purges of Stalin. And he was thrown in a gulag for about 8 years. Okay, so By 1931, he founded the Group of Investigation for Reactive Motion. That's a shout out to Newton's third law of reactive motion, equal reactions. Okay. It developed the first Soviet liquid-fueled rockets, what they called the GERD 9 and 10. In 38, it was taken over by the military and became known as RN2. Also in 38, which is the year that World War II broke out, Stalin purges the attacked rocket scientists. A guy named Valentin Glusko was the premier rocket engine designer. And you're going to find out in this book that Glusko and Korolev hated each other venomously. Okay? And that was really a downfall of their system because during the moon race they had a falling out, which basically was responsible for that big N1 explosion in the end that I told you about, where they lost 150 engineers. Okay, so Valentin Glusko is arrested. And part of the way that you can exonerate yourself is to make a confession and to point out other people that are traitors. We did this in the United States with McCarthyism. You were brought before the Senate hearing committee, and you were supposed to give names. Then you could be set free. If you gave names, you could be set free. If you didn't give names, then you could be put in jail. I do believe I see people texting, and I know I'm boring, but unless it's an emergency, you can wait, and you're still texting. Okay. Now, basically, these two men became bitter rivals because guess what? Glusko denounced Korolev. Korolev was beaten, tortured, signed a confession, gave up other names, then he was sent to Siberia for 8 years or 10 years of hard labor. He basically became emancipated, lost a lot of his teeth. It was a horrific time. People didn't survive. People slept in ditches and just died left and right. Somehow he survived it, made many, many pleas, writing letters to Stalin, his wife writing letters, etc. He became estranged from his wife and his daughter almost for life. Anyway, finally, he got released. And when they released him, the story is great in the book. Do you think that they said, here's a train ticket home? No. They kick him out in the snow at the front of the gate, and that's it. No coat, no nothing. He almost died. The only thing that saved him, he said, was that he found a loaf of warm bread sitting out on a curb one night. And that was what saved his life. He would have died the next morning. One of those things where you think, a message from God came down. It's like an angel put it there. Type of experience. Okay. Anyway, they keep him under house arrest, and he does work in Moscow for years. But in 1944, as the war's coming to an end, they realize that this guy's a genius, and they got to get him involved. So he gets promoted to a team of rocket scientists, and he's given 3 days to propose the Soviet equivalent of the German V2, for which he's going to steal the parts. So he's sent. After that, he's sent to Germany, and he's supposed to grab everything he can from the Germans, including rocket scientists and equipment. And as they didn't get nearly the booty that the United States did, but they were very clever in the way they did this. They grabbed the scientists and whatever half-built parts they could find or destroyed parts, and they brought the scientists, and they had the scientists redraw all the designs for them and got new blueprints from the minds of all these scientists, rocket scientists, and then they sent them back to Germany. We're done with you. Okay. Not to mention they dragged them out of their houses at 1 in the morning after they had them get morning drunk at a party. Okay. Great stories in this book. Okay. Still political prisoner, he's promoted to the chief engineer, charged to design and build the Soviet equivalent of the V2, and he built something called the R1. We ended up calling it the Scud. In 1953, he begins the development of the world's first intercontinental ballistic, 7,000-kilometer range, and carry a 5-ton payload based upon stacked stages. This is the R7 rocket right here. This is what launched the first human into space. It's what launched the first satellite into space. Now, what was I going to say? Oh, yeah. There was a nuclear scientist, I can't remember his name, and he was asked by the military, how much does a nuclear bomb weigh? You know, a hydrogen bomb. And they hadn't built the hydrogen bomb, a version that could fit on the rocket yet. And so he just said 5 tons. Well, ladies and gentlemen, that 5-ton declaration, which was a guess, changed history. Okay? In the United States, we were building nuclear bombs for missiles, being launched on missiles that were a lot lighter. So we didn't need to build as strong rockets with as powerful of thrust. Okay? We could get the warhead there on a rocket that could never actually get to space. It wasn't that powerful. With a 5-ton mandate to go 7,000 kilometers, he had to build one hell of a powerful rocket. And he realized that if you put something that only weighed, say, 2,000 pounds on the top of it, that he could put it in space, into orbit. So he built himself a rocket that could put things into orbit, because that's what he dreamed about. He dreamed about going to the moon, putting men in space, working in space. He would have gone himself if he could have. Okay? But he used the idea of building ICBMs as a mechanism of doing it. So why did the Soviets get to orbit before we did? Because they had to have heavier lift capability, because the Soviet military had dictated a 5-ton lift capability for 7,000 kilometers. August 57 is the first successful launch. He instantly goes and says, I want to put something in space. And by October, while he's doing 7 or 8 other projects, October 4th, he launches Sputnik. And Sputnik then now goes around the world every 90 minutes. There's the launch picture itself of the R-7 lifting Sputnik up. It is just a small little sphere. It weighs, where's the weight? 183 pounds. It's a foot in diameter, and all it has is a radio transmitter. Okay, it orbited between 130 and 500 or 600 miles. It takes about an hour and a half to get around. It did about 1,440 orbits over 3 months, and then it burned up as it re-entered the atmosphere. Okay. What Orlov did was he put a radio transmitter in it that transmitted at the frequency of all of the amateur radio operators used in the United States. This meant that anybody who had a ham radio could listen to Sputnik beep. And listen they did. Okay? And so it panicked the entire United States. Am I supposed to stop now? I think I am. Yeah? 25 after? Okay. So what we're going to do now, when we come back, is we're going to talk about the reaction of the United States. And this moment is so defining of the United States that things like NASA were formed, school systems were completely revamped, completely from the bottom up. It's hard to. I mean, they literally reinvented the way that they did elementary school and high school and things like that. So I'm going to show you some of that stuff when we come back. All right, you guys take care.